But for now, I want to talk a little bit about projectivities as functions. In other words, I want to look at projectivities of the real line to itself. Because when we have a projectivity of the real line to itself, we can think of that as a function from R to R. And in doing so, we'll see that some familiar operations on the real numbers can be realized or constructed as projectivities from the real line to itself. So let's let capital L, I want to stick with this capital L notation, so let's let capital L denote the x-axis in the Cartesian coordinate plane, which we think of as an extended plane. So we have points at infinity lying out beyond our sight, out in the distance. So it's really an extended plane, but we still have Cartesian coordinates on it. So this is 0, 0, this is 1, 0, this is 0, 1. We have the usual R2 Cartesian coordinate system. And let's look at some projectivities from L to itself, from the x-axis to itself. So the first example that I want to look at, which is an example / exercise, because I'm not going to fully verify it. I'm leaving it to you to verify that what I'm saying here is true. So the first example is that given this diagram here, which we'll look into a little more deeply in a second, given this diagram, the perspectivities FO1, so that's the perspectivity centered at O1, from L to M, followed by the perspectivity centered at O2 from M back to L, that projectivity, that composition, it gives you the function x goes to 2x. So this is a dilation or a scaling function which doubles everything. It's a doubling function. And I'm claiming that this projectivity I've constructed here, I'm claiming that this projectivity that I've constructed here, that it as a map from the x-axis to itself, as a map from the real line to itself, takes any real number and doubles it. So let's see why that's true. So let's just look at the number 1, 0 first. Let me change my color. Let's look at So let's look at this number 1, 0. So let's think of that as the number 1 on the real line. So FO1, what does it do? Well, it's projecting this point over to this point here. And I'll use the laser pointer. It's projecting this point to this point here. That's what FO1 is doing on M. What is this point? Well, you can work out that it's 1.5, comma 1/2. Though M, by the way, is a line y equals 1/2. It's another horizontal line. So it's projecting this point up to this point, 1.5, comma 1/2. Then our second perspectivity, centered at O2, is projecting this line back to L, and it's projecting it to the point 2, 0. So it's taking 1, 0 to 2, 0, or as a function of the real numbers, it's taking 1 to 2. And I claim that it's generally taking x to 2x for any x. So I'll leave it for you to verify, but maybe just to see another example, here's the point 1/2. Let's just see where that appears to go. It appears to go here from the first perspectivity, and it appears to go this way through the second perspectivity. And indeed, it looks like it goes to 1, more or less, but I'll leave it to you to algebraically verify that. And similarly, 0, that's a bit easier to verify. It goes up to here via the first perspectivity, and back down to here via the second perspectivity. So 0 goes to 0. Here's a question that maybe is a little more interesting. Where does this, so let's assume this is indeed x goes to 2x. You still have to do a little work, but maybe for a general point, say x comma 0, check algebraically where it gets sent to through this sequence of 2 perspectivities. So that's the exercise. Now, assuming that's true, assuming that this is this function, where does it take infinity? Actually, don't even need to assume it's this function. I mean, just from the construction itself, let's see where does this projectivity take the point at infinity. Well, remember how we, in last week, maybe, hopefully you remember, but just to refresh your memory, how do we figure out where perspectivity sends a point at infinity? Well, the key is to draw a line through the center of perspectivity, which is in that class of that point at infinity. But here, that was in the 2D case. Now we're in the 1D case, where there's a single point at infinity, which I'm denoting by the infinity symbol. So, and that the class corresponding to that point at infinity is just the class of horizontal lines. So to find out where the point at infinity, so we have to draw a line through O1 that hits the point at infinity of L. So to do that, we have to draw a horizontal line through O1. And we have to see where that line hits M to see where the line at infinity in O1 is going to. But this horizontal line doesn't actually hit M in the plane. It intersects M at infinity. So it's taking, in other words, it's taking the point at infinity in L to the point at infinity in M, because they share the same point at infinity, because they're parallel to each other. L infinity equals M infinity. And this, and this horizontal line through O1, it's hitting this point L infinity. So it's fixing it. So infinity goes to infinity, and infinity is a fixed point of this projectivity x goes to 2x. Now, is it the only fixed point, or are there other fixed points? Well, we just mentioned it, so maybe you remember that we just mentioned another fixed point, namely 0. 0 goes up to here, and then back down to here, so 0 goes to 0. So there's actually 2 fixed points. Are there any other fixed points? Well, some familiarity with this function will tell you that no, there are not. There are no other real numbers that are fixed by the doubling function besides 0. And in this case, infinity is also fixed. So we have 2 fixed points of this extended line under this projectivity. And in general, a projectivity from an extended line to itself is called hyperbolic, small typo there, hyperbolic, if it has exactly 2 fixed points. So this is an example of a hyperbolic projectivity from the line L to itself. Okay, let's look at a second example, this time of the function x goes to x plus 1. So let's first look at this construction here, which I claim represents this function x goes to x plus 1. So how to see that? Well, where is 0, 0 going to? O1 is pulling 0, 0 up to here. So by the way, M is once again, I should have written this, but M is once again the point y equals 1/2. That's what our line M is. So what is O1 doing? Well, it's pulling 0, 0 up to this point. What is that point? Well, it's actually 1/4, 1/2. You can work that out because O1 is at 1/2, 1. This is a line with slope 2. So, so the first projectivity, FO1, it maps 0, 0 up to 1/4, 1/2. The second projectivity, it's going to push this point down to 1, 0. So we're mapping 0 to 1. Similarly, what's happening with -1? Well, or maybe we'll do, let's do -1. So -1 maps, is pulled up to this point via FO1, and then via FO2 it's pushed down to 0. So -1 maps to 0. So you can verify for yourself algebraically that this construction here actually represents the function x goes to x plus 1. And part of that will be on the homework assignment as well, so do take a look at that. For now, we'll accept it as a fact and ask the question, okay, we accept this. This is a construction. We can realize this as a projectivity. How many fixed points does this projectivity have? Well, as a function of the real numbers, x goes to x plus 1, the standard translation by a unit, has how many fixed points? Well, none. You're translating everything along. Nothing can possibly be fixed. So there's no fixed points for the real version, real numbers version of this. But now we're on the extended line. We have a point at infinity. Where is the point at infinity going? Well, once again, we can figure that out by looking at the horizontal line through O1 and the horizontal line through O2. Oh, I just realized I made a small mistake earlier. I mean, I didn't finish my explanation for why infinity is a fixed point in this example. I showed that the point at infinity in L is taken to the point at infinity in M by O1, and that they are the same. Basically, that O1 fixes that common point of infinity. But you can easily see that O2 does the same thing. We can draw the horizontal line through O2. That's also fixing M infinity, which is equal to L infinity. So the projectivity fixes it as well. The composition of those fixes that as well. Okay, going back to here. Here, there's a single line, horizontal line I can draw between O1 and O2. And for similar reasons, we can see that the point at infinity is fixed by O1, and it's fixed by O2, and indeed, M infinity is equal to L infinity again. They share one point at infinity, and that's fixed by both of these perspectivities. So the projectivity fixes it. So we do have a fixed point, the point at infinity. But we only have one fixed point in this case. And in general, a projectivity from an extended line to itself is called parabolic if it has exactly one fixed point. So earlier, with two fixed points, it's hyperbolic. With one fixed point, it's parabolic. And let's see one third example. And this is another function. X goes to 1 over x. By the way, these functions aren't fully random. There's a reason that I'm choosing these functions to look at as projectivities, and we'll see why. So let's look at x goes to 1 over x. I claim that this construction, and I know these constructions are getting a bit weirder and weirder, this one does take some time to sit with. I don't expect you to just look at it and think, aha, it's 1 over x. You need to spend about a few minutes working it out. And I'm not going to do that right now, so that's an exercise. That's the exercise part. But maybe we will at least we'll at least see that it works on this point, 2. Where does 2 go to? Well, O1, let's just visually see, it pulls it down to here, and O2 pulls it up to here, and 2 goes to 1/2. So 2 goes to 1 over 2. Similarly, 1, let's just see another example, 1 here, well, the projectivity through O1 does nothing, because O1 is fixed. It's on both capital L and little m. Sorry, this point here is fixed. It's on the intersection. So the FO1 does nothing to it. What about FO2? Well, FO2 also does nothing, because it's, again, on the intersection of little m and capital L. So 1 is fixed. So we've seen that 1 is fixed. We've seen that 2 goes to 1/2. And maybe one more thing to quickly check, where does infinity go in this case? This is a little bit more interesting. So capital L, we can see that the point at infinity, we can see where it gets mapped to by drawing a horizontal line through O1. That hits capital L at its point at infinity, L infinity. But where does it map that to? It maps it to a regular point on the line little m. It doesn't map it to the point at infinity for little m. Rather, it maps it to this regular point of little m, 2 minus 1. So infinity is finally not fixed in this case. Infinity, L infinity, is mapped to the point 2 minus 1. And then I'll leave it to you to verify that this is indeed the map x goes to 1 over x. But, and also to just check that sorry, I didn't finish what I was saying again. Let me just finish what I was saying, which is that, okay, FO1 takes L infinity to 2 minus 1. What does FO2 do to 2 minus 1? We have to see where it ends up. Remember, we were looking at the projectivity, so we want to see where FO2 now sends 2 minus 1 in order to see really where infinity goes. Well, for that, we need to draw a line between 2 minus 1 and O2. O2 is negative 2, 1. So the line connecting negative 2, 1 and 2, negative 1 is just this line, which goes through 0, 0, which hits L at the point 0. So infinity, L infinity is actually going to 0, 0. So infinity is getting sent to 0. So I'll leave it to you to check, and we've checked that the construction fixes 1. I'll leave it to you to check that it sends 0 to infinity. That part I'll leave for you to check. And more generally, how many fixed points are there? Well, we can use the fact that we know this function, a little bit about this function. How many fixed points does this function have? Well, there's only one, the point 1. And throwing infinity into the mix doesn't give us any extra fixed points. We just saw that infinity goes to 0. And similarly, 0 should go to infinity. So there's a single fixed point. So this is another example of a parabolic projectivity. Remember, 2 fixed points is hyperbolic, 1 fixed point is parabolic. Now, in general, a projectivity of an extended line to itself is called elliptic if there are no fixed points, if there are 0 fixed points. So as a challenge, this is a challenge exercise, can you construct an elliptic projectivity on this line L? Construct a projectivity that honestly has no fixed points. Remember, translation doesn't work because translation fixes the point at infinity. We want a projectivity of the extended line which has no fixed points, including the point at infinity can't be fixed. So this is a bit tough. It's not the easiest thing to do, but it's an interesting exercise. And it's a pretty hard exercise, except I'm going to give you a hint, which will make it, hopefully, quite a bit easier. So my hint is the following. Choose any 3 points, A, B, C, and any 3 points are fine. I've drawn them evenly spaced, but they don't have to be evenly spaced. They can be any 3 points. And construct a projectivity that permutes them cyclically. For example, you could send A to B, B to C, and C to A. That's an example of a cyclic permutation of these 3 points. And how do you do that construction? Well, we saw that you can always construct a projectivity that takes any 3 points to any other 3 points. Here we only have one line, though. So it might be helpful to first project these 3 points onto, onto another line. Let's call it little l. And let's just project from, we can just choose any center of perspectivity we want, and we can project over here, and that'll give us, we'll call this little a, little b, and little c. And now, using the construction we've already seen, you can now map A, B, and C via another projectivity to capital A, capital B, and capital C, but permuting the order. You can now find a projectivity that sends little a to B, little b to capital C, and little c to capital A. So I'll leave it as an exercise to construct that projectivity that taken together with this purple projectivity here, let's call this O1. So FO1 followed by this green projectivity together is a projectivity that'll permute these A, B, and C cyclically. So that is relatively easy. We know how to do it, it's just a matter of working it out. But the harder part now is to prove that this map, which permutes A, B, and C, actually has no fixed points anywhere. Clearly A, B, and C are permuted cyclically. None of those are fixed. But I claim that this map will have no fixed points at all, anywhere, including infinity, including 0, anywhere you look. So in other words, it's an example of an elliptic projectivity. So that's just, I'm leaving that as a challenge for you to see if you can construct that and prove that it's indeed elliptic. And so now we've looked at, we've looked at a bunch of projectivities that capture functions of R2. And so far we've only looked at perspectivities centered at ordinary points of R2. But I just want to mention that we can also, there's nothing to stop us from considering perspectivities whose centers lie at infinity, at different points at infinity. And when we do that, here's an example of that, we end up mimicking parallel projection. We do something that's essentially, because our center of projectivity is infinitely far away, the lines from that are all going to appear parallel to each other. Remember, any point on this ordinary plane, when we connect it to a fixed point at infinity, is going to give us a line in that parallel class corresponding to that point at infinity. So they're all going to be parallel to this line here, which is defining the point at infinity that I've chosen. So the advantage to doing this is that we can construct perspectivities that mimic parallel projection. This is parallel projection, what you're seeing here. You're just projecting by parallel rays of light. And this simplifies many constructions. So this is a useful thing to be able to do, parallel projection, as opposed to only doing central projection, which always does some distortion. Parallel projection is a lot more friendly when it comes to certain Euclidean notions. So it doesn't distort it doesn't distort ratios, is the right way to say it, I guess. Whereas central projection distorts ratios and creates a lot of overall distortion to deal with. So it's nice to be able to do parallel projection, but for that we need points at infinity to be our centers of perspectivity. On the other hand, the disadvantage is that if we're using points at infinity for our perspectivities, then we can no longer do these constructions with a straight edge alone. Up until now, all of these constructions I've been doing, all these functions I've been constructing, I can do these constructions just using a straight edge. No need for a compass, no need for a ruler or a measuring device. I'm just using a straight edge. So that's kind of cool, that these are constructions that you can do with a straight edge alone. We're not taking any measurements, except for, I mean, we are given a coordinate plane. We're starting with kind of a God-given real line with measurements on it, but we're not using a measurement device beyond that. We're just using a straight edge. So it's not a major disadvantage, but it's something to keep in mind, that if we're doing parallel projection, we can't do that with a straight edge alone. But let's see that disadvantage aside, let's take a look at the advantages. Let's see how this function x goes to x plus 1 can be represented by perspectivities centered at points at infinity. So I will just we'll use the following picture. Let's take this point at infinity here, and through parallel projection, we send 0 to, this is just a slope 1 line here, and via parallel projection, by this slope 1 line, I'm sending 0 to 1, 1, 1, 0 to 2, 1. And now we can do parallel projection via, let me just say it a little more clearly. So that as a perspectivity, this is FO1 from L to M with center O1 equal to this point at infinity. And sorry, why am I saying slope 1? I should be saying slope 1/2. These are all lines with slope. Oh, no, sorry. They're lines with slope 1. Yeah. This should read slope 1. And we're taking 0, 0 to 1, 1, 1, 0 to 2, 1, etc. It's just a 45-degree angle. It's just slope 1. And next, we just parallel project everything down via lines like this. So we follow it with a perspectivity FO2 from, another typo here, from M back down to L with center O2, which is the point at infinity corresponding to the set of vertical lines. And that'll just take 1, 1 to 1, 0, 2, 1 to 2, 0, and taken together, we're mapping 0, 0 to 1, 0. We're mapping 1, 0 to 2, 0. So this is a little easier to see why this is translation. It's actually much easier to see. So that's the advantage to thinking of translation as given by this projectivity here. So as an exercise, can you simplify the constructions of the function x goes to 2x and x goes to 1 over x using perspectivities centered at infinity? In other words, it's using parallel projection. Okay, now I have a question. We have special names for projectivities that fix 0 points, 1 point, and 2 points. 0 points is elliptic, 1 point is parabolic, 2 points is hyperbolic. What about projectivities that fix 3 or more points? So for example, a projectivity that fixes A, B, and C, does it also get a special name? And the answer is kind of. If a projectivity from a line L to itself fixes 3 or more distinct points, then it is the identity map on L. So it's kind of a special name, it's the identity. If it fixes 3 or more points, it fixes every point, which is why we're calling this the 3 fixed points theorem. If a projectivity from a line to itself fixes 3 distinct points, it fixes every point on that line. And when I say line here, I really mean an extended line. So the line includes a point at infinity. That's important to keep in mind. And just a quick illustration of this, here's a projectivity that fixes 3 points. So first, I'm looking at FO1 from L1 to L2, so that's taking A, B, and C down to these points here. Next, FO2 from L2 to L3, that's taking these points to these 3 points here. And finally, FO3 from L3 to L1, back to L1, takes these 3 points, projects them up to these original 3 points here. So A, B, and C are going back to A, B, and C in that order, no permutations of them. A is going back to A, B is going back to B, C is going back to C. So they're fixed points. So according to the theorem, this projectivity must be the identity map. That's the content of the 3 fixed points theorem. So how do we prove this? There's actually several possible approaches. There's many different proofs. And this turns out to be a very crucial result. So there's many ways of approaching it. And we're going to sketch 2 proofs of it right now. And in the upcoming lecture, or actually maybe the next to next lecture, we'll prove it fully using a 3rd approach. So right now, let's give 2 sketches. And I'm going to leave some, each sketch is going to have a gap, which I'll leave for you to fill, but they're a bit non-trivial. So, which is why I don't want to call it a complete proof, and we're not going to use these proofs in the course. We'll do a 3rd proof, which we'll do fully after this. So the first proof sketch uses something called a linear fractional function. So this is my linear fractional function proof. And how does this work? Well, we've already constructed several real functions of the real line using projectivities. We've seen that the following functions can be constructed as projectivities. X goes to ax, x goes to x plus b, and x goes to 1 over x. Okay, so I'm exaggerating a little. We saw x goes to 2x, and we saw x goes to x plus 1. But it's not much of a stretch to imagine you can alter our constructions a little bit to get any real number a, any non-zero real number a as your scaling factor, and any real number b as your translation factor. So I'll leave that for you to verify, but using these constructions we've already seen, it's pretty easy to get any of these functions as projectivities. Putting these together, what other functions can we get? So taking combinations of these 3 functions, composing them, basically composing these functions, that's what I'm allowing. Taking these 3 types of functions and composing them as many times as you want in any order. What other functions can we get? And it turns out there's a nice name for those and a nice structure for the entire class of functions that's generated by these 3. Namely, they're linear fractional functions. And they look like this. X goes to ax plus b over cx plus d, where AD minus BC is non-zero. I guess technically speaking, AD minus BC being non-zero makes it an interesting linear fractional function. If AD minus BC equals 0, then what happens? Let's just check that quickly. If AD minus BC equals 0, then, then we have a problem actually, because then the numerator is going to be a scalar multiple of the denominator. And what will happen then? Well, in that case, we're just going to get a constant. The x's will cancel out, and we'll get that x is going to a constant. So that's not a particularly interesting function. And yeah, I guess we don't want to call that a linear fractional function. So we'll exclude this case where AD minus BC equals 0. But how do we see that composing these functions gives us a function of this form? So that requires some algebraic manipulation. Namely, you can rewrite this standard linear fractional function in this form over here, which is more clearly a composition of these three types of functions that I mentioned. In particular, you can take x, you can multiply it by c, so you can do a dilation of it, then you can add d, you can do a translation, followed by another dilation by c, followed by a reciprocation, you put it in the denominator, followed by scaling by the constant bc minus ad. After that, you can translate by a over c. So it's a composition of these three types of functions when it's written this way. And you can work out for yourself that these two expressions are indeed equal to each other. So what this shows is that any linear fractional function can be realized as a projectivity, because any linear fractional function can be written as a composition of these three types of functions. And these three types of functions are all constructible as projectivities. Therefore, any linear fractional function can be constructed as a sequence of many, many, many perspectivities, as a projectivity. So, the interesting thing, which is harder to see, is that any projectivity realizes a linear fractional function. We've seen that any linear fractional function can be constructed as a projectivity. But conversely, any projectivity you create, no matter how complicated, from a line to itself, from the real line to itself, is actually capturing some linear fractional function. It can be written down concretely as a linear fractional function. So the challenge, what I'm not going to do, which I'm leaving as a kind of challenge exercise, is to try and prove this by putting coordinates on two lines in R2 and working out a general equation for a perspectivity between them. So if you're interested in trying this, a nice reference is the book 4 Pillars of Geometry by Stilwell, in which he doesn't completely finish this proof, but he does it as a series of exercises which might help you out if you're trying to do this. So I'd recommend that book. And why does this matter? So let's assume this is true. Projectivities from a line to itself are basically the same thing as linear fractional functions, if that line has coordinates, if it's the real line. Why does this matter? And why does this help us prove the 3 fixed point theorem? Remember, that's what we're trying to prove. Well, what are the fixed points of a linear fractional function? They're just the solutions to this equation. And we can easily rewrite that. We multiply both sides by cx plus d and combine like terms. And that gives us cx squared plus d minus ax minus b equals 0. This nice quadratic equation, how many solutions does it have? The solutions to this are precisely the fixed points of the linear fractional function. Well, okay, there's a special case to consider. This could be the case that A equals D, so this is 0, and B and C are also 0, in which case upstairs here, if B and C are 0 and if A equals D, this just becomes x equals x. And yet downstairs also we see that we get 0 equals 0. So same thing. So in that case, there's infinitely many solutions because in that case, we're really just looking at the identity function. If A equals D and B equals C equals 0, then this is just the identity function. So then there's infinitely many solutions. On the other hand, if that's not the case, you can solve this equation and there's at most 2 solutions. So there's at most 2 fixed points. There cannot be 3 or more fixed points without it being the full identity function. So that solves, that proves the 3 fixed point theorem. Modulo that challenge exercise, which I'll leave for you. Okay, so let's see another proof sketch. The second proof sketch I want to look at, I'm calling the Harmonic Net Sketch. And this is going to be a totally different proof than the linear fractional function proof. Coming at it from a completely different direction. And in order to fully finish it, it'll be helpful if you've had a course in real analysis. And for example, but in fact, you'll kind of need that to fully complete the proof. But it's interesting to think about even if you haven't had a course in analysis. So I want to just describe it. So remember that a point P, we'll say that a point P is harmonically related to 3 collinear points, A, B, and C, if we can write a sequence of points beginning with A, B, and C, and ending with P, such that each point in the sequence forms a harmonic tetrad with 3 previous points in the sequence, some 3 previous points. Any 3 can be used in any order. So remember harmonic tetrads, it means that a harmonic tetrad is related by a diagram like this. There has to be there are a set of collinear points. There's a quadrilateral whose sides converge to A and C respectively, and whose diagonals hit B and C, hit that line AC in the points B and D. So in this case, we see that from this picture, we see that the point D is harmonically related to A, B, and C. Or A is harmonically related to B, C, and D. B is harmonically related to A, C, and D. Actually, all of those are true. Okay, let's try and make another point that's harmonically related to these. Let's try and let's draw a point here, and let's take let's do our harmonic tetrad construction. So we get another quadrilateral here, and oops, I messed up. I am getting the same point A again because remember, I'm using the that's the entire coincidence of harmonic tetrads. This is again, I'm looking here at the harmonic conjugate to C with respect to B and D, which is just going to be A. So I kind of messed up. I didn't choose well. Let's do that again. I'll stick with this point, but now let me let's do let's take these 2 points and let's connect C to both of them and D to both of them. Okay, so that's going to give us this very small quadrilateral here. Oh wait. Sorry. There we go. Yeah. Now this is not. Yeah, this is our quadrilateral, and when we connect up these 2 points, we end up with a new point here, which I can call E. So E is harmonically related to B, C, and D. And so on. We can keep adding new points this way that are harmonically related to existing points by doing more and more of these harmonic relations. And it's obviously kind of cumbersome to actually do, but the interesting thing is that we can consider the set of all points generated by A, B, and C harmonically, which is called the harmonic net of A, B, and C. And it consists of all points harmonically related to A, B, and C. And as a challenge, can we prove that a harmonic net is dense in the real line? Basically, the point is that we can keep adding more and more points to this harmonic net. And I'll just do a couple more. This is getting kind of messy, but let's see, here's another point here, F, and so on. You can keep doing this construction and adding more and more points, and I claim that this harmonic net that we generate is dense in the real line. Between any two points, there's a new point which is harmonically related to A, B, and C. And I'm not going to prove that. Proving it does require some work, and there's actually many different approaches to this proof. So it's a fun thing to think about, and I'll leave it to you to do that. But let's assume that it's dense. Why does that matter? Well, if a projectivity fixes 3 points, A, B, and C, we know that it fixes all the points in its harmonic net, since perspectivities preserve harmonic relations. That's what we saw last week. So harmonic nets are fixed under, if a projectivity goes from a line to itself and fixes 3 points, it's going to fix an entire dense harmonic net. And that's kind of a big deal because perspectivities are continuous. That, too, you have to prove. We haven't actually proved that. But if we believe that, then we have a continuous map fixing a dense subset of the real line, which then has to be the identity. So that's a completely different type of proof of the three fixed point theorem using harmonic nets and harmonic tetrads. And as I said, we're going to give a complete proof of the three fixed points theorem in the final week of the course. So not in the next class, but the following class, using a third strategy, in particular using the cross ratio. But in the upcoming lecture, we're going to assume that this theorem holds, and we're going to see just how powerful it really is. In particular, it's going to allow us to finally prove Pappus's theorem, which we learned in the first week of the course. And we're also going to learn a theorem called the fundamental theorem of projective geometry, which is going to really give us a better sense of what changes when we shift perspective, how many things are changing, and how much control we have over those changes. So thank you, and see you in the next class.